Knowing the force that a current carrying conductor experiences in the vicinity of a uniform magnetic field now allows us to calculate the total force that a circuit would experience if it is in a region of uniform magnetic field. In this example, we want to find the total force that acts on the straight and curved sections of the conducting loop shown in the screen. We start by calculating the total force acting on the straight section. If we look at a tiny element of the straight section, here represented by the vector ds, where ds points in the direction of current flow, we can calculate the tiny amount of force on this section of the straight wire from our expression for the force that a straight conductor experiences in a uniform magnetic field. Everywhere on the straight section of the wire, the orientation between the current flow direction and the magnetic field is the same, which means everywhere on the straight section of the wire we find that the force on each infinitesimally small section ds is just given by the current times the magnetic field times the infinitesimally small length ds, all pointing in the positive z direction. To find the total force on the straight section, we add up all the forces on all the individual small infinitesimal elements ds, which just constitutes an integral over the entire length of the straight section of the conductor. Given that the current and the magnetic field are constant, and that the orientation of ds and the magnetic field is also constant over the entire straight section of the conductor, the only variable in the integrand is ds itself. We know if we calculate the integral of ds, so if we add up all the lengths of all the little elements ds, we must just end up with the length of the straight section of wire itself. The length of the straight section of wire is just equal to 2 times the radius of the circular section, which all together gives us the expression for the total force shown on the bottom of the screen. Therefore, we've got a force equals to 2 times the current times the radius times the magnetic field magnitude pointing out of the screen. For the curved section of wire, the calculation now becomes more complicated. Again, we choose an infinitesimally small element of the conducting wire somewhere on the curved section of the conductor. However, we note 2 things now. First of all, ds does not point along any of our principal axes. Second of all, depending on where I choose ds on the curved section of the conductor, the orientation between ds and the magnetic field changes. The solution to this problem is to try and write the general expression for the force that the little element ds on the curved section experiences in terms of a single variable. Here we will show that an appropriate variable to choose is just the angle theta as shown on the screen. The first simplification we make is to write the cross product between an arbitrary element ds on the curved section and the magnetic field vector as just the current times ds times the magnitude of the magnetic field times the sine of the angle between the two, and from the right-hand rule we know this cross product will point into the page. No matter where we choose ds on the arc, the cross product between ds and the magnetic field will always give us some vector pointing into the page. However, the magnitude of this vector now depends on the angle theta. We can write ds itself as a function of theta by noting the relationship between a length of arc and the angle subtending it. We can, if we add up together all the forces acting on all the tiny elements ds that make out the arc, this implies an integral over the entire arc. So this means an integral spanning the angles theta equals 0 to theta equals pi radians. In our integrand, the only variable is sine theta, and if we integrate sine theta between the limits shown, we just end up with a total force pointing into the screen with magnitude 2 times the current times the radius of the arc times the magnitude of the magnetic field. Therefore, we've got